Welcome back, everyone. We're to section 3.2, where we are introducing the idea of the integral. And we're going to deal, first of all, with the fundamental theorem of calculus. There's actually two parts to the fundamental theorem of calculus. This is the first part. And it says if we have the integral of f prime of x dx, then the integral and the derivative part of it cancel each other out. So they're inverses of one another, they undo one another. Typical notation that we would use for this would be the capital F of x and evaluated from a to b. And then that's going to equal capital F evaluated at b minus capital F evaluated at a. So we're now dealing with something called the antiderivative. And it sounds exactly the way that it is. It is the opposite of a derivative. So if we go in one direction with a derivative, what is the opposite direction that we want to go? Meaning, if we have a function f prime of x equals 2x, then that means that f of x is the opposite of that, or x squared. Meaning the derivative of f of x, which is 2x, x squared, pardon me, the derivative of f of x, which is x squared, becomes 2x. So the derivative goes this way. And the antiderivative goes this way. Oops. Goes this way. And let's move into our definition. So an antiderivative of the function f of x is any function capital F of x where f prime of x equals f of x. So in other words, we're going backwards. And if you remember the power rule, for derivatives, was here. The power rule for the integral is the opposite. We'll talk about the plus c here in just a minute. The antiderivative of function f of x is a whole family of functions. And what we're going to run into is f of x and then the plus c. The reason, and c is any constant, and the reason that we need that plus c when we're dealing with what's called an indefinite integral. And by the way, the fundamental theorem of calculus is what we call a definite integral, meaning there are boundaries a and b, whereas the indefinite means that there are no boundaries. So we will need that plus c. And the reason is, the reason is if I take the derivative of x to the third minus 4, that is 3x squared. If I take the derivative of x to the third plus pi, that's still 3x squared. Now, the issue that we're running into is when we start with 3x squared, we want to go backwards. We don't know if it's plus or minus some constant, minus 4 plus pi or whatever. So in general, we just say plus c. And we just are making a statement that we're dealing with any arbitrary constant that needs to fit there. Sometimes we can pick the constant, and other times we will have information to come up with a specific constant. All right, so we have the integral symbol. Again, that's that elongated, weird-looking s. And let's find an antiderivative of 2x. So an antiderivative of 2x is going to be x squared plus 5. Another one, another antiderivative that we could get could be x squared minus 17 halves. Another one could be x squared plus pi. So we can have all sorts of antiderivatives. So here are a bunch of specific antiderivatives. But a generalized antiderivative is going to be x squared plus c. And that C can be any constant in the whole world we want it to be, unless there's a reason why we need to specify a specific constant. But we do need to include that plus C as part of the answer. So now we know that the derivative of e to the x is just e to the x. So its antiderivative is going to be here. E to the x and then the plus C, of course. Here's the other part of the fundamental theorem of calculus. It says the area is equal to the integral from a to x of f of t dt. By the way, the t is what we refer to as a dummy variable, meaning it's just sort of a placeholder until we get there. And so when we take the derivative of that, the t gets the x, and the derivative and the integral cancel out. They kind of undo one another. And so if I take the derivative, so here, on my example here, if f of x equals the integral from -1 to x of t to the fourth dt, then the derivative of that is going to be x to the fourth power. And the derivative of that evaluated at 4 is going to be 4 to the fourth power, which is 256. All right, and so let's get an idea of what we're talking about when we talk about area under a curve. So here we have the graph of f prime of f of t is shown below. And we want to know whether there's a maximum and minimum values. And we're going to start here. Again, we're looking for maximum and minimum positive area. And I want to point out that, let's see if I can do this. No, that's not what I meant. Stop. Okay, let's see if I can. Nope, I'm not even going to try. Okay. All right. So we have, stop. Oh my God. Okay. Let's see if I can do this now. Yeah, okay. So here is my positive area. Here. Let me turn that off 1 second. All right. So we have our positive area, and I want to point out that we have a minimum positive area at x equals 0. Because at x equals 0, we have no area. However, we have a maximum positive area at, this should be t, not x, t, at t equals 3. And you'll note down here that we have negative area. So that is definitely a low for us. Let's do another illustration of this. Let's move on to our graph here. So we have negative area here. This is all negative area. So the most negative area that we have is going to be a min at 2, because at 2, that gives us the largest amount of negative area. However, at 4, we end up with the largest amount of positive area. Even if we have more negative area up to there, then we have more negative area after 4, which means we have another minimum at 6. And it says to restrict our answers from 0 to 6. So again, we're just talking about positive and negative area here. If the derivative f prime of x is positive, and it's increasing. Now, if it's increasing, that means for sure we are going to be increasing. We're going to be concave up, because that means the second derivative is going to be positive. However, because f prime of x is positive, that means that f of x is increasing. So our answer is the increasing and concave up in this case. Again, the increasing means that f double prime is positive, which means concave up. And because f prime is positive, that means that f is increasing, right? So that means that we have a function that's here. Nope. Let's fix this. So we have a function here, and it is increasing, which means we are, let's do different color. That means we are here. And f prime is increasing, which means that we are going to be, f double prime is positive, which means we're concave up. And our last part here. So we're given that f double prime is, or f single prime is x plus 4, x minus x plus 2. This means x plus 4 equals 0, x plus 2 equals 0. These are our critical values. And if we take the second derivative, I have to use the product rule. So 1 times x plus 2 plus 1 times x plus 4. This gives us 2x plus 6. And specifically at 4, which is where they ask us to evaluate this, we get 2 times 4 plus 6, which is 14. And the point is it's positive. So it's concave up. So this is increasing. And concave up. At 4. Yeah. All right. And the next video is going to be a little bit less abstract and hopefully a bit more on topic. So here we go.